Hey guys, can I get a sound check?
Yeah, we can hear you.
Okay, great, thanks. Okay. All right, guys. I've got project one on Canvas. Hopefully, you guys can access it. Let me know if you can't. I was gonna walk through it a little bit and sort of hopefully it'll be a pretty, I'm hoping it'll be a simple, relatively simple project as like sort of a warm-up. So let me go, let's see. I think it's this here. Can you guys see the, like a PDF document? It says 91 project1.pdf?
Yes.
Okay, great. So let's see. So here's the initial thing here is the how to report, create the report on your project. Along with our report, etc. I want to ask you guys to use basically presentation slides, to get used to using presentation slides as for your project reporting. And I would like you guys to have the following format. The first page, and I think this is generally good practice that I've found. So the first page, title, the project name, your name and email address. That's because a lot of times in the real world, your PowerPoint presentation will get a life of its own. It'll be stored for future use, or somebody else will get it when you're not there to present it. And if there are questions and so on, you want to make sure they have your name and email address so they can contact you. So that's always good practice to have that in your first page. Second page, right off the bat, you want to just have a short introduction. Really, the second page and the third page are very key. So the third page is what I call, I always put, whenever I communicate to people in the form of a report, it could be an email, Word document, PowerPoint slides, always put an executive summary section. Executive summary is just a distilled, description of what it is you did, what happened, why, those kind of things. Just imagine if you're, you were going to send it, I don't know, you were going to send your presentation to the department chair. I don't know if you guys know, I've never met her personally. I'm trying to think of somebody who's like, you guys can visualize in your lives that you've met, but is maybe like several layers removed from what you're doing for this class. Like, the department chair is not particularly wants to get into the nitty-gritty details of a report you're writing for a project in a class in her department. But she might want to know something about what it is we're doing in this class, something about you. Maybe you've applied for, a job in her office or something. So that's for her, right? Somebody at that level who's tech savvy, engineering savvy, understands the stuff, but you want to just give her a one-pager about what this thing is about. And if they don't read anything else, in this document, they'll understand what you've been up to. Last page is, is a conclusion. This is also very important because a lot of times what I see are PowerPoint slides that are just a bunch of slides put together. Every presentation, every report, every document you create, every email you write has to have a narrative. You're trying to either, inform something, or you're trying to like sell your idea or persuade. Okay, either way, you need to have a narrative. It just can't be a bunch of data without an explanation, without a reason why you did it. And conclusion is another important place, the last slide, to say why you did it and why. And then the results, again, I see a lot of presentation slides, even from very skilled engineers, that just have, this is number 5 there, that just has like a graph. There's just like a title, like, I don't know, rise time of inverter, and it's just a graph. It doesn't say like, is this the rise time I was expecting? Is there something off? Why do I think there is a discrepancy? Should, other people be alarmed? Does this mean everything's like okay and we're good? Am I suggesting that we do some follow-up? That a lot of times that's missing, and you have, every slide has to have your story. What are you trying to say? Are you telling the rest of the crew, the management, whoever is looking at this document, whether they should be concerned, they shouldn't be concerned, like everything's okay, or you need additional resources, whatever your message is. And the last thing that, again, I've seen a lot, even with experienced engineers, is not good labels, just straight up labels on axes and titles of graphs, etc. So these are really important hints for your presentation slides. Something, I'll leave it up to you guys how many pages is between the conclusion and the executive summary, which is the 3rd page to the conclusion is the last page. Something like this, I would say maybe like 10 slides or something. We'll see. It depends on what you're trying to, I think each one of these things you may want to do like 1 or 2 slides on each one of these things. Okay, so like I mentioned, we're going to have a theme to our projects. And the theme to our projects is going to be output buffers. We're going to start by looking at what a buffer just looks, an inverting buffer looks like in a driving a load inside the chip. So here's the idea. Let me just read it for you guys, and then I'll show you. I also have a template LT Spice file up in Canvas, so you guys can download that and start playing around with it, and use it as a starting point. So hopefully that'll help set you off in the right direction. You don't have to struggle too much with LT Spice or anything like that. So okay, so the first step is I'm giving you a starting point, which is the width of your NMOS transistor in your inverter, and that's an individualized width. So what you do is you take your student ID number. Here's an example. I guess it's 9 digits or something. So you add up all the digits, divide it by 10, and that becomes the width of your NMOS. That's just like a starting point, okay, that we're going to start with this project, and that's going to evolve over time to take us to where we're going. So that's the width of your NMOS. Starting with that, I'm asking you guys as the first step to select the, you could either do simulations at that point or just start with your first, good estimate, and pick a length for the NMOS. So you've already got your width, pick a length, and then you pick a width and length for the PMOS transistors. And there are a bunch of other transistor parameters, area source, area drain. We're going to get to these later, but right now you can just leave them blank. And then I'm asking you guys to justify your choices. Just, why did you pick those numbers? So that's the initial step. Number 2 is the DC transfer function. So this is voltage in versus voltage out. Here we're looking for noise margins, and I'm asking you guys to explain how different this is than the noise margin of an ideal inverter. Okay. The third part, we're going to get to the meat of the problem. So you're going to basically use the inverter that you come up with to drive another inverter exactly like itself. So whatever sizing you come up with here, I'm assuming you guys can see my cursor. You should use whatever sizing you come up with inverter 1, you should use that to drive inverter 2, and also this capacitance in the middle. This capacitance, there's always a line, an interconnection line between, there has to be a physical line, a physical piece of metal between inverter 1 and inverter 2. Inside the chip, it's going to be a aluminum or copper line, and it'll have some capacitance. Okay, so this is what your schematic kind of ends up looking like for the delay simulations. And kind of telling you guys to drive this inverter with a certain voltage source, with a certain rise and fall time. And that I'm already kind of doing that in the LT Spice, so hopefully you don't have to do a lot of thinking there. And then what am I doing? And I'm asking you guys to initially use a capacitance of 10 femtofarads for the C-int. So you're driving yourself, an inverter like yourself, plus this intermediate capacitance with this voltage source that has a certain rise and fall times. I didn't mention it, but the voltage source should go between 0 and 1.8 volt, because as you'll see, the spice deck we're using for these projects is for a 0.18 micron process, and that has a 1.8 volt supply. And then I want you guys to plot and state the propagation delay for the rising trip, propagation delay falling, rise and fall time number, and for inverter 1. Okay, and hopefully we'll get around to what these things are fairly soon here. A lot of this info tonight and then Tuesday. And then finally, so this number, so I'm asking you guys to drive this thing as if it was a sort of a 50% duty clock that's running at 200 megahertz frequency. This is what this pulse period of 5 nanoseconds represents. And then what I'm asking you guys to do is to increase this capacitance, C-int. You're going to keep cranking that up till this signal path fails somehow. And I'm asking you to make sure you keep an eye on both failure, what could be happening on this int, as well as V out, and describing what that failure looks like. Why do you think that's the point where it fails at whatever capacitance you pick, and what does it look like? What happened? So having described all that stuff, let me let's see. Let me see if I have. Let me pop up the simulation. Here's this guy. So you guys should be seeing LT Spice schematic. Okay, everybody see that? So I'm assuming that you guys see it. So I have.
Yeah, we see it, Professor.
Okay, great. Thank you. So, I did this a boneheaded way. A better way to is actually make a symbol so I can play around with it. But anyway, so I've got one hint, by the way, is to use a separate power supply for each of these inverters, because in sort of, we're going to be taking this schematic and modifying it for project 2 and 3. And that'll sort of just a little bit of help, that'd be somewhat helpful. By the way, one hint is, I mean, I've already drawn this for you guys, but a lot of times, for whatever reason, when people start doing simulations with CMOS, they forget how to hook up the substrate connection appropriately. So I've got it hooked up for you guys, but just, I don't know, for future effort, I just seen that things go wrong a lot. So in LT Spice, can you guys see my cursor?
Yeah.
Okay, great. So in LT Spice, you actually, one thing I like about it a lot is you actually can put the model file for the transistors for your devices right in the same sheet. So that's this model file here. Whoops. This model file over here. This is the model for the NMOS. And this is the model for the PMOS. And this is just a format for a SPICE transistor model. I don't know if you guys have seen this or not. It's level 7, whatever that means. It's for the TSMC 180 nanometer process. And that's a 1.8 volt supply process. The reason I picked it is because it's, the model files are easily available online. I could just cut and paste it for our class. Okay, so to begin with, what I have is, so there's this stuff, this written stuff has the models. It's got a few other things, but the main things you guys are going to play with. I mean, so first thing is I would go through and size your transistor. So this transistor, I took my ID number, I summed all the digits, divided by 10, and end up with 3.2 micron width. Okay, so that was my starting point. Then I picked a certain length for this guy. And then using those numbers, I picked a certain width length for the PMOS. Okay, so that was my starting point. Next thing was to do a DC operating point analysis. Okay, so basically sweep this, I want to sweep this input and plot it against this output to look at noise margins, etc., and see how it compares to a ideal inverter. So I use this .dc. If you guys look at the second line, .dc, and this voltage source is called VGSN, and I'm sweeping it from 0 to 1.8 volts in 0.01 volt increments. And then, so this is, by the way, I don't know if you guys have played with LT Spice. You're welcome to use other forms of Spice to do this. It's just that this is the only one I have access to. I'm okay if you guys go ahead, but like I really won't be able to really be very helpful if you do use PSpice or something else. And the interface for the PC looks different. It's a little bit better than the Mac interface, but I can see your files. If you guys run into any problems, you can send me the files and I can try to help debug it. Anyway, so here's the Mac interface. So I'm just going to simulate, and I'm going to just plot this guy. And you see, I've got, actually you can't see, let's see, let's put it here. Okay, so now you see a transfer curve. Horizontal axis is VGSN, which was the input to the inverter. The vertical axis is the output of the inverter, and you see this inverter transfer function that you expect. When the input is low, the output is high. When the input high, the input is low, and you're making this transition somewhere. So the ideal point, as we'll see, I think we described this a little bit, is like exactly as 1/2 VDD. So it'd be 0.9 volts, but this is pretty close. I mean, it looks just right off the bat with the numbers. I didn't tweak the numbers. I promise you, because my first guess is it looks pretty decent, not bad. So it's sort of around 0.9. So I don't know, like looks okay. So you could try to tweak it a little bit, center it a little bit more, which is good. Okay, so now as a next step, whoops, are you guys, let me go back. to this guy. Okay, so now that was, I think, what was it? Problem 2. Problem 3, I'm gonna needed a transient simulation. So I'm gonna go and asterisk and spice means you are commenting out a line. So I'm going to take out the asterisks in the .trans statement. Trans statement is for transient simulations. You're telling it to do a transient simulation for 20 nanoseconds instead of a DC operating point. And let me pop into this guy. And so this voltage source VGSN is a pulse voltage source. The initial value is 0. When it turns on, it has a value of 1.8 volts. It waits 2.5 nanoseconds before it does anything. Has a rise and fall time of 100 picoseconds or 0.1 nanoseconds. Be careful here if you put, for whatever reason, SPICE doesn't like spaces between the numbers and the N or the P or whatever format you guys are putting in. So it has to be 0.1 N, for example, without a space. I don't think it likes 0.1 space N. Okay, so just beware of that. And the period is 5 nanoseconds. So let me do a simulation, and then I'm going to plot. I'm just going to plot the input just so you guys can see it. So this guy, yeah, okay. So this is what that waveform was. It waits 2.5 nanoseconds at 0. So remember, we had a T delay of 2.5 nanoseconds. It goes high to a value of 1.8 volts. That was T on. Oh, sorry, that was V on. And stays there for 2.5 nanoseconds. That was, I think, T on. And then the fall is another 0.1 nanoseconds. And the period from, the one rise to the next rise is 5 nanoseconds. And my total simulation time was 20 nanoseconds. So that's what I get for my input. Okay, so now let's look at the output of this inverter. So I have, let me actually change this because I have a ton of capacitance at the moment. So I'm going to change this to be, I'm telling you guys to start with 10 femtofarads as the starting capacitance. So let me resim the 10 femto. Okay, so the green is the input to that inverter, and blue is the output of the inverter. And then so you see, like, you have the blue has a certain rise, it's inverting the input, it has a certain rise and fall time. There's a certain propagation delay from the input, the green changing to where the 50% point of the green to the 50% point of the output. It's doing some funky stuff here and here, which we'll talk about later. And then I'm going to plot the output of the second inverter. Okay, and that's the output of the second inverter is the red. But it gets harder to see here. Let's wait for me to stack this stuff up. I'm not sure, but let me zoom in here. So the green is the input of the first inverter. It gets inverted in this blue curve, and then it hits the second inverter, and the second inverter also inverts. So the output of the second inverter has the same polarity as the input voltage, but as you can see, there is like a certain delay there. Okay, and notice how, like, the rise time, for the sake of discussion, compare the rise time, the fall time of the blue to the rise time of the red. For the sake of discussion, assume the rise and fall time for the inverter are the same, which there's no guarantee it will be, but for just this discussion, assume they're the same. I mean, designed to be the same, the rise and fall times. Notice that the blue has a much longer fall time than the red's rise time. It's because the blue, this inverter, is loaded down with the 10 femtofarad capacitance and another inverter like itself, whereas the second inverter isn't loaded down with anything, so it just sort of jams. Okay, gets very fast. Okay, so now I'm going to start increasing the capacitance of CMOS. Okay, so I'm going to increase it to 100 femtofarads and resimulate. So now this is with 100 femtofarad capacitance for CNT. Still nothing horrible is happening. It's still working. So, blue again is the intermediate node. The rise fall times have gotten a little longer with 100 femtofarads for CNT, but still works okay. So I'm going to start cranking up. Take CNT to 500 femto. So now we see that, okay, at 500 femto, now the blue is starting to get like the rise time is getting pretty long, like starting to get a little alarming. I mean, it's getting to be the reason, at some point, so, let's say you want to pass a 200 megahertz signal through these two inverters. This is still pretty acceptable. Usually what people say is, like a rise time, well, depends on a lot of things. But rise fall time is about like a quarter of the period of the clock is still okay. So that's kind of like almost like a triangle wave. That's probably overdoing it. But anyway, this is still looks okay at 500 femto. So I'm gonna crank up to 1 picofarad in between. So I'm basically taking these steps like what you guys should be doing in the project. There I'm plotting them. So now let's share. Now it's looking pretty hairy. Look at the intermediate point. You don't quite get a real one here. I'd say this is like not, yeah, I wouldn't take this as something that's really passing a good 200 megahertz signal. It's just not achieving a full, I mean, it's sort of getting to the full value, but it's really questionable, right? It's kind of like just touching 1.8 volts barely. Looks like the fall time is still pretty good. It's coming down. Like a zero value stays zero for a pretty good while, but the one value is not valid for you could say it's not valid for long enough. Now notice still that the second inverter is cleaning up as like a good inverter, as a good logic gauge should do, is cleaning up the blue. So it's still, gets a good rise and fall times again, because it's not loaded down. Okay. So if you just look at the output, just a hint, if you just look at the output of the second inverter, you could fool yourself into thinking everything's okay, whereas your intermediate node is really is not working properly. So let me simulate again. So now I got 1.5 puff, 1.5 picofarads, and I would say this is definitely something that is not working. You know, this rise fall times is just not fast enough to deal with this period. Any questions, guys? I'm throwing a lot of stuff at you.
None so far.
Okay. So
guess
this
just
one, I mean,
I
I
just have
feel
like a
like I'm
generic
giving
question.
you guys the templates and all this good stuff. So I wasn't going to give you guys a whole lot of time to do it. So
Professor,
yeah, go ahead. Sorry.
I think someone has a question actually.
Oh, thanks.
Yeah, I just had like a generic question.
Sure.
Is this like, this is individual project, correct? This
Yes.
individual work or is it a group?
You guys are welcome to work with each other, but each one you'll have at your own inverter size. So if you run into
Okay.
problems, you're welcome to
Yeah,
get
so
help.
we all still have to submit like our own based off
Yes.
our Bronco ID. Got it.
That's
Yeah.
correct. Let's see. So basically, I was going to ask you guys to turn this thing in, not this coming Tuesday, but then the Tuesday after, which is, I guess in 10 days or 9 days. What does that end up being? See all my cool stuff I don't have. October 8th. So it'd be October 20th to turn it in. I'll put that on the web. So I'll give you guys kind of like, I guess the way I look at it, I always used to get projects done on the weekend. So it gives you guys 2 weekends, so or whatever. I don't have to do it on the weekend. If you want.
Professor, I had another
Yeah.
question.
Go ahead.
So like when we're considering like our rise times and fall times, or
Yeah.
more so like the rise time, I guess, in this case with so the second inverter rise time, would we base that off of like our input signal? So say like we start our rise time at as soon as input signal goes high, or should we start it where we start to see it transition? Because then that's that delay where it's still flatlined in your graph or whatever. Like red is still flatlined way past green already going high. So should we consider that into rise time? Or should it just be based off of whenever we see it transitioning from like a stable to rise or fall?
Yeah, or you're asking about like giving the rise and fall times for the
Yeah,
presentation?
for like the
Yeah.
rise and fall times of red,
Yeah,
would we start from, so say we're at 0 volts and then go to 1.8 at the
Yeah.
0 volts? Do we account the difference between like the input swing as well?
yeah. So I don't know, let me know if this doesn't answer your question, but the first thing is, for the rise and fall times and all that stuff, you're only looking around the first inverter. The second inverter is just acting like you're sort of loading down the first inverter.
Oh, okay.
To get a reasonable. So everything is for the first inverter is like the business end of like what we're trying to do.
Okay.
So now let me I hope, between now and today and Tuesday, we're going to get some definitions of these stuff. And maybe, I don't know if we already talked about these, maybe we didn't. Let me just draw some stuff for you guys. Let's see.
Professor?
Yeah.
So if we work on this as like a group, then would we be like submitting the same thing, like a same PowerPoint?
No, you wouldn't be. You'd have your own PowerPoint. So you'd be like working as a group would be if like you can't quite figure out why your simulation isn't working or the general parameters, but each person is submitting their own PowerPoint presentations based on their own transistor size.
Oh, okay.
But like if you run into trouble or you want to kind of simulate together or whatever, that's fine. Okay, so let's see. Okay. Hello. Power Mancurian. Can you guys assume you can't see my,
Yeah, we can't see it. It says that you started screen sharing, but it's stuck on that.
why? Let me kill it. Show content screen. Okay, so we're gonna go into this stuff, slide deck, maybe, I guess it'd be slide deck 7 or something, talks about a little bit about this. Maybe we talked about it somewhat before, but let me just draw this stuff for you guys. So we have 2 inverters. So we have inverter 1, and then we have inverter 2, and then we have some capacitance, and then we have an input to this guy. This node is called int for interconnect. This is, V out, or I forgot what I called that one. So all the measurements happen around this guy. Okay, so this dude is just acting, this guy and this guy are acting as a load for that input. So, a lot of times, again, your circuits, as we'll see, I mean, the main thing this project is going to show you guys, or the series of projects, is how external things affect your circuit. They start, like, if I had nothing here, this thing would be like happily jamming. You'd be able to drive this guy hundreds of megahertz, maybe gigahertz, I don't know. But as soon as you start putting some load on it, and then we'll start loading it in different ways, you'll see it starts, like, things start going downhill pretty fast. So anyway, this stuff is just a load. So we're doing the measurements around here. And so let's say my input looks like this. So I'm going to assume my input is like very, very fast. Transitioning very fast. Assume it's transitioning infinitely fast. And this is time. This is voltage. So this is, in our case, this is 1.8 volts. Normally it'd just be VDD, whatever the VDD supply is. For my VDD, if this was a 65 nanometer process, we'd be using a 1 volt VDD. But in this particular case, again, it's a 180 nanometer process, and we're using a 1.8 volt VDD. And that will stay with us for the rest of the projects. Okay, so the output of this point, okay, so int, if I draw int, it's gonna look like this. I'm gonna draw kind of an extreme case. So it's inverting from here. So I drew this falling edge of this guy really badly. Assume it's happening very quickly. So it's inverting, so it's going to do that. So this is int, and this guy was Vn. Okay, so here are the definitions. There is propagation delay. And then there is rise fall time. Okay, propagation delay is a measure of how long the transition, so roughly it's a measure of the time from when this guy changes to when the output changes. Okay, so it's measured between the input and the output. What does that mean? Let's use this guy. So basically, I'm measuring the difference between this point, which is the 50% point of input transitioning, to the 50% point of the output transitioning. So it's measuring the difference between the input and output changing. So this is prop delay, PD, fall. There's a falling prop delay and a rising prop delay. The rising prop delay is here, and it just refers to the output rising or falling. This is an inverter. We have to pick, the input's doing the opposite of the output. So PD rise the prop delay rise is referring to when the input changes 50% of input to output changing 50%. And that they may be different. Prop delay fall might be different than prop delay rise. Okay, depends on the sizing of the transistors and so on. Okay, then the rise fall time is measured just at the output. So it's not the difference between the input and output, is just at the output. So now let's look at what the fall time looks like. So if I just kind of look at the fall time, it's when the output is falling, and it's specified from the 90% point of VDD. Yeah. So from the time the output goes to 90% of the VDD to 10% of VDD. Okay, so notice I'm not really even looking at the input. So this is T fall. It's a fall time. Okay, and then the rise time is from the output going from 10% to 90%. And this is rise time. So again, I'm not looking at the input, I'm just looking at the output curve and how it's changing. So those are the 4 numbers you need to specify. I think it's problem number 3 in the project. By the way, this is just for the sake of completion in this book here. It's pretty typical that you define rise fall times as 10 to 90%. Some people define as 20% to 80%, but people will always tell you this is like the 1090 rise, this is the 2080 rise. I don't know if there is, I can really honestly say there is a standard, but it's usually one of those two. It's either 1090 or 2080. Yeah, I don't know why there's a difference, but the prop delay is always from 50% point of the input to 50% point of the output. Clayton, did that answer your question?
Yeah, that makes more sense now. Thank you.
Okay, sure. No. What else do I want to say? I think that's all I have to say for the projects. Any other questions, guys? Okay, sounds good. So let's so go on for. And by the way, there's I think I have a YouTube for LT Spice. So Alexandria is asking about what you're going to be working on in groups. that's like a report that I'll be, asking you guys to get going pretty soon here. So that's different than the project. So we don't have midterms, finals, whatever, or homeworks. We have just the projects and a report comparing two processors. But for the report, unfortunately, can't do any simulations or anything. Does that answer your question, Alexandria? Okay, great. Let's see. Yeah, anyway, I think I mentioned there's LT Spice. Hopefully it's pretty straightforward. I'm hoping you guys have had experience with Spice. Okay, so, okay, guys. What should I do? What should I do? I think I'm just going to jump into slide deck 7. I think we had a few, I think we went pretty much to slide deck 6. There's a few things, but I think I might just, the right place to circle back on those is during the projects. So we'll do that. So I'm just going to jump into slide deck 7. Okay, so we're gonna start talking about some of these tools you need to do this project. So DC response, logic level, transient response, RC delay, etc. for a CMOS, and focused on a CMOS inverter. Okay, I'm gonna what do I want to do with this? Really nothing much. Don't use past transistors. Well, we can come back to this later, but I just want to kind of get into the nitty-gritty details of a CMOS inverter. Okay, so where we started was that we said we were just started by pretending our NMOS transistors were like switches, and same thing with our PMOS transistors. And as we saw in the slide deck 6 and 5, they are anything but. They're these sort of complex 3-terminal devices that actually 4-terminal when you look at the body. They are doing all sorts of stuff. They're going through various states as the input switches. So it's not like, first of all, the input here is not, so we're going from a logic or binary model of the world where signals basically go from 0 to 1 or 1 to 0 infinitely fast. They just change. And then the outputs or the transistors just act like switches with very low or zero resistance. They have zero input capacitance. It's just a switch. It's either on or off. But in reality, that's not what it's like. So in reality, what happens is if I look at a CMOS inverter, I guess there's one drawn here. The input is transitioning from low to high and high to low. And a logic level, as we've mentioned before, is 0 to VDD and VDD to 0. So logic level high is VDD, logic level low is 0. Okay, so if you look at what these transistors are doing in the meanwhile, like let's just look at the NMOS transistor. When this thing is happening, the output is doing the reverse. So this output, if you plot this output, is doing this. By the way, this is like time. So, when the input is low, the output is high. So I'm just, if this is, so this, let's call this let's call this T equal to T0, and this is T equal to T0. Okay, so these should be superimposed. This guy should be down here, kind of doing the reverse. But if you so look at this rise versus the output falling. These are happening roughly at the same time, except with some delay. Maybe I should just to not have it be too confusing. I'm gonna do this. So this is V out, and this is Vn. So let's look at what happens when Vn, this part of time where the input is been 0 for a while. When the input's been 0 for a while, the input to the NMOS is 0. So that means its VGS of this guy is 0. That means this guy is off. The VGS of the PMOS, so this is 0, this is VDD. The gate source voltage is minus VDD. And, we didn't really talk about the PMOS so much. Maybe we did a little bit in slide deck 5. We just said sort of everything is inverted. But when this guy gets a minus VDD VGS, it turns on, so it's on. And the output is VDD. It's basically this guy's been on here. This guy's been on for a while and has pulled this node to VDD. So the output is at VDD at this point. As now this guy is going to transition from the input Vn, is going to transition from a low to a high now. Let's see what happens. So nothing happens and we're going to talk in detail about this. So I'm just giving you guys the punchline ahead of time. As this input starts transitioning, the VGS, notice the VGS, this input is the VGS for the NMOS. So the gate source for the NMOS is starting to increase as this guy is going up. Okay, so it's starting to go up at some point, and the VGS for this guy is starting to go down, right? It's this point is now at 0.1 volt, at 0.2 volt, at 0.3 volts. At some point, this guy, this VGS or this input is going to go over a threshold voltage for the NMOS, and the NMOS is going to turn on. Okay, as soon as this input goes above a threshold voltage for the NMOS, it's going to turn on. The PMOS is still on, okay, although its VGS has been shrinking, but it's still over a threshold voltage, like around here we're talking about, something like that. Now what happens is this guy's on, but remember what it looks like is something like this. If I look at, the question is what's the current through it? Okay, it's going to try to pull this output down, but how much current? Remember that if I plot the current through this NMOS, it's going to have different curves for different VGSs. So let's say this is VGS of, let's say the threshold voltage of this device is, I don't know, 0.5 volts. Okay, so let's say this is VGS of 0.6 volts, and this is VGS of 1.2 volts for the sake of discussion. Okay, so what happens, this is all for the NMOS. So my VGS is going up. So my VGS is moving this way. My VGS is going up. So my VGS is changing curves continuously, getting more current. And notice initially this output, so that's what the VGSs are doing. They're going up from curve to curve, but this voltage here is the VDS. And so initially, so here, as this guy turns on, my VDS is pretty high for this NMOS, right? The output is at VDD. So that's the drain is at VDD. The source is at ground. So my VDS is very high, my VGS is fairly low. So I'm going to be kind of right around here. Okay. Now, as VGS goes up, this NMOS is simultaneously pulling its drain voltage down by discharging this capacitance. Okay, so my VDS is going down and I'm moving up in VGS. That means I'm going to start here, then I'm going to work my way to here, and then sort of the next graph. So I'm going to start, this guy's going to start in saturation. Then it's going to start walking its way towards linear. And at some point, it's going to have a VGS of 1.8 volts at the ultimate end. Like when you get to here, the gate source voltage of this guy is going to be 1.8 volts. And at this point, the drain source is going to be fairly low. So I'm going to end up here in the linear part of this curve. And then eventually it's going to drive this point to ground. Okay, so basically that's kind of what's going on with the different transitions. So when, what do I want to say? Okay, so that's like what happens. And notice that because, so this inverter is driving other CMOS logic gates. It's driving God knows what, inverters, NAND gates, NOR gates, whatever they may be. Sorry, I put a NOR gate there. NAND gate looks like this. So, but this is very critical. We've mentioned a couple of times, all these inputs are purely capacitive. They're not going to be outputting any current back into this NMOS. So this NMOS is just, all it's doing is discharging this total capacitance. So it's going to go all the way to zero. But the model for this load is purely capacitive. And it has, it's a nonlinear capacitance, because as the voltages on the inputs of these gates changes, they go from being off to going into inversion. And where we saw that in a MOS transistor, when you go from the transistor being off to when it has a channel, the capacitance increases significantly. So it's a nonlinear capacitance that these two transistors are driving. So this guy's pumping current into this nonlinear capacitor. This guy's pumping current out of the nonlinear capacitor, not at the same time. Well, in the transient situation, they're on for a brief moment of time, just during this rise and fall times. But the rest of the time, when it's at the logic 0 or logic 1, either one of them is on or the other one. So these capacitance change, but they remain purely capacitance. So what does that mean? Well, that means that if you think about Kirchhoff's current laws, so KCL, I forgot if Kirchhoff was CHO, I think it's CH. So you guys may be having like nervous breakdowns remembering Kirchhoff's current laws. Basically says that sort of all the currents coming into the node have to be the same as the currents going out of the node. So this basically, we only have this node, okay, only has two currents. The current coming out through the NMOS and the current going up through the PMOS. Okay, and these two always, so because of Kirchhoff's current laws, they have to be the same. So we're going to use that to figure out like what this transient response looks like and what the transfer function looks like. So we're going to use Kirchhoff's current laws. Okay, so right now we're just going to look at the DC response. So that means sweeping the input, seeing how the output changes with the input. So we want to look at we want to plot not things as a function of time, but as a function of V in versus V out. And we're hoping, ideally, we're hoping for a curve like this. At this point being VDD over 2, this being VDD, and somewhere out here being VDD. Okay, so we're going to see what happens. Now, one thing we could do is do what I was just doing. We could step through these VGSs, and for each one, figure out what the VDS is, use that to calculate the currents, and solve basically a bunch of two simultaneous equations. Okay, what are those equations? They're equations for IDS. So would be either beta over 2 VGS minus 4 for the really basic case, not including the second, third order effects. Okay, we could solve, basically these are the two values for IDS, one for N, one for P. At each point, we would get a number for the IDS for N and one for P, set them equal to each other, and calculate what the VGSs are. So we could do that. And in fact, that's what SPICE is doing to some extent. But it turns out that doing a graphical solution gives you more insight. Now, before I do this graphical solution, one question I have from you guys is, are you guys familiar with like load line analysis or looking at things like a load line? Anybody not familiar, not heard of load lines? Derek, you haven't heard of load lines, no? That means no, you haven't heard of
No, definitely not.
Okay. So let's see, what is a load line? So a load line is sort of a graphical way of figuring out what are the valid points of a circuit. Okay. So let's say, for me anyway, it's easier to like think of it as like, as it give the example case of a resistor and say an NMOS transistor. Okay, this has the same thing, that the current, if there's no resistive load, and we just have these two guys in our circuit, the current at this node, the current going through the resistor has to be the same as the current going through the NMOS transistor. Okay, so that's like Kirchhoff's current laws. So one thing we could do is to draw the various, so if I was this is VDS, or this could be, let's say, I'm gonna call it V out, which in this case is the same as VDS for the NMOS. Okay, and this is the current, so I'm going to call that IX, right? So that's the current that goes through both the resistor and the NMOS. So let's assume that this has a certain voltage. So V sub G is something. So V sub G is equal to V sub G1. And that's going to give me a certain curve here. So there's a range of valid values for V out. We don't know what it is, but this is for VGS is equal to VGS1. Okay. Now notice that, so a load line analysis is you basically, so this gives you the range of permissible currents and voltages for this device. And on top of this, I want to superimpose the range of voltage and current values for this device. What am I trying to do that is because where those two curves intersect is the only possible solution for what's this VDS value. Because why were they intersect? It's because at the intersection point, the current through the resistor and the transistor are the same, okay, between those two graphs. So we said that's our assumption, right? We got Kirchhoff's current laws. So it has this current and this current have to be the same. So, and okay, so that's, and before let me draw something and then we guys can, hopefully it'll make more sense. Now, the tricky part of this is because the direction of the voltages and currents are reversed for the NMOS and the PMOS. So for the NMOS, for this current, I'm drawing it like this. But because the resistor is hooked up like this direction of voltage versus current is reversed for this because I'm drawing V out versus, sorry, I didn't draw VDD here. So what I want to draw is V out minus VDD. Minus VDD, right? That's basically my current. I sub X is V out minus VDD over R. Oh, I hope I don't get that one right. Wrong, sorry, wrong. So look at what the points are here, right? So initially when, do I want to say that? VDD, no, I'm sorry. I did draw it wrong. So it's VDD minus V out. Okay, so let's take a couple of cases. When V out is 0, basically we have VDD over R is the current. So it'll be like it's VDD over R. And when V out is VDD, Ix is equal to 0. So it'll be like 0 here. So no, not 0. So this is V out is VDD, but basically the current's going to be 0. And the slope of this guy is going to be 1 over R. Okay, so usually we're used to seeing, sorry, resistance slope being kind of like this with 1 over R, but I'm not plotting, I'm plotting V out here. I'm not plotting VDD minus V out. So that's why it's sort of flipped over here. Do you guys see what why I drew it like that?
Yeah.
Okay, so it's a little bit of a mind bender, maybe the first time you see it. But so the only place that these two nodes have the same value of I sub X is this point here. Okay. I sub X same for R and NMOS. Okay, so this is a graphical approach to solving this equation. I guess I could have tried to, write the equation for this current, write the equation for that guy, and solve it numerically, or I could just draw the two transfer curves and see where they intersect. And as, like, for example, as this VG goes up, so let's say I go to VGS2, which is higher than VGS1. I'm going to draw that sort of qualitatively. Now the only intersection point between the resistor and VGS2 is going to be this guy. So that says VDS, my output is dropping as my VGS goes up. The output is going from here to here. Okay, so as I sweep VG, make it higher and higher, my output is just wherever I'm intersecting. Let's say I'm going to draw something VGS, VGS 3 is less than VGS 1. So I'm going to draw it like that. So that's going to have, so these are like the values for the output. So you guys see what I'm doing there? Kind of, again, it's it just basically, I'm saying the only permissible points is where the two curves cross, because the currents have to be the same. And as I change my gate source voltage, that gives me only a single value for V output voltage. That's a possible solution to this problem, to the Kirchhoff's current law problem. And I'm doing it graphically. Derek, Tyler, did that make any sense?
Yeah, I don't get like why we do this. What's the point of it?
So otherwise you would have to, let's say, what would you do if you wanted to figure it out? You would do, well, I have ID S, or I should say IX is either beta over 2 VGS minus VT squared, or beta VGS minus VT minus VDS over 2 VDS. And IX for R is VDD minus V out over R. So what I would have to do then is to solve two simultaneous. First of all, I would have to figure out like which equation to use for each VGS, right? So I have a VGS. I'm gonna, so let's say VGS 1. I would first decide if I'm in saturation or linear, and then make that equal to this, and algebraically solve for V out for each
Okay, that
point.
makes sense. Yeah,
So
that makes sense.
yeah, so this is doing exactly the same thing, except it's a graphical representation. It's really sort of you're drawing a numerical technique, whether you're doing it this way or this way. It turns out in some circuits, and I believe I agree with this, that especially in the case of the CMOS inverter, this sometimes gives you, this sometimes basically gives you a little bit more insight. It's sort of a little bit of a brain tease, because if you change your resistor values, they'll start like doing this, right? Kind of give you different curves, so you can kind of, maybe it helps you tune this thing. Now, in the case of a CMOS inverter, is particularly useful, as we'll see. But whoops. Kind of ran out of time with that, but let's so anyway, so hold this thought for Tuesday about doing load line analysis, and we're going to apply this to the CMOS inverter. And again, as sort of a punchline type of thing, we're going to basically look at the transfer function for the NMOS and superimpose the transfer function for the PMOS on the same graph, and where they intersect is for each VGS, because notice that the gates are connected together. So for each VGS, we only have one permissible value for VDS or the output. And basically plotting those, you get the transfer function of like what's of V in versus V out. And we'll go through and see how that works. Okay, guys, I'm going to stop it here. If you guys have any questions on the project, just shoot me an email or whatever. Yep. Any questions? Nope. Okay, I'll let you guys go. Have a good weekend, guys. Take care.
Thank you, Professor.
Thanks. Bye.
Take care, Professor.